Yeah, so as I said in last week when you were in class, all of the videos for the days you're not here are posted up on YouTube. So no, it's not the first page. If you flip to the second page, there's practice problems, and then flip to the next one, and there's a blank page. Unfortunately, this is the one electronic copy of the one set of notes that I do not have. So it's just that blank page, and you'll have to fill it in as we go through it. I'm sorry, everything else is all laid out for the rest of the year. I've tried finding this, and I can't find it. Yeah, so you'll write these notes on the blank page. I'm sorry, I don't always intend for this to be this way. I have a channel. You need to just keep looking at my channel. If you're subscribed onto it, you'll get notifications as they come. So I've already started recording, Mohammed. Shh. You seen Hetem? Shh. So yesterday I talked about gravitational forces. You've seen the force of gravity already, but we just talked about it in more general terms. So do you remember the force of gravity from the last unit when we talked about just forces? What was it? Yeah, so force of gravity equals mass times the acceleration due to gravity. Yesterday I showed in more general terms what it's equal to. So you'll need to watch the video to be able to understand that, because I'm not going through it today. What's that? I don't know. So like I said, all of you who complained about doing a flipped classroom last semester, Hassan, congratulations. You don't have to write this down if you don't want to, but these are your notes. T, would you like to explain what I just said about the notes? Thank you. So, everything that is on here you'll want to write down. You can write them in nice little boxes for every slide if you want to do it that way. You're the third person to ask me that since I've started recording. Anyone else want to ask where to write the notes? Ahmed, there should be, what are you doing? Yes, this is recording. So the group ones are going to have a great time watching this video because they get to hear about this entire first part where I just have to answer the same question over and over again and still get you guys quiet. Well, Fuad, if I repeat exactly what you say, yes, they can hear it. So, to explain how two bodies that are not in contact, meaning not physically in contact, how they interact with each other, we use a concept that's called fields. So for instance, how many of you actually watched the video yesterday?
How much of the video?
The entirety of it. Okay, so you will need to catch up on that. It's your choice how you catch up on it. The completed notes are put up online, but you need to stay caught up because everything today builds off of yesterday. So if you did nothing about yesterday, you're now going to be 2 classes behind because this won't make sense. So when you're not at school, it's not a day off. You still have a responsibility to do work. So with forces of gravity, we talked about how you and the person beside you are actually attracting each other with the force of gravity. So any 2 objects with mass will pull each other together, but they're not actually touching. So we use the concept of fields to be able to describe this. So we've got a bunch of different types of field: gravity, magnets, electrostatics. Magnet and electrostatic we get into a little bit next year, but not this year. We mostly just talk about gravitational. So what is a field? Well, basically, it's like a sphere of influence that is affecting all the objects around it. So you cannot see it, you cannot touch it, but it influences things that are around it. So how it affects the objects around it depends on, well, it depends on which type we're talking about, but it also depends on the distance. So the closer you are to something with a mass, you experience a greater force of gravity. So this is why if you saw on the first slide, I'll come back to this. So if you're still writing, I'll come back. The first slide, like I said, I'll go back. So like, if you notice here, a person at 3 different positions on the Earth has 3 different weights. If you're at the equator, you'd weigh 978, whereas if you're in the UK, 981, and if you're at the North Pole, 983. Very minor change, but this changes depending on where you are. And this is because when the Earth is spinning, it's wider at the equator, or near the equator, than it is at the poles. And that's just based on inertia pulling this object, the Earth, out as it spins. Pardon me? So will your weight change? Yes. Yeah, so weight depends on your mass, which won't change, times the acceleration due to gravity, which we're talking about today. No. No. When you weigh yourself on the scale, you're actually not measuring your mass. You're measuring your weight. It assumes no, it's not, but it's a really simple conversion between the two. So if you took your scale and you measured yourself here, and if you took your scale and you measured yourself on the moon, they'd be different. If you went and took a scale to the top of Mount Everest, it would show a different weight. Because what's happening when you stand on a scale? It's measuring how much the scale has to push upwards because the force of gravity is pulling downwards.
Isn't it the same force of gravity on Mount Everest?
Not quite. It's the same equation, however, as you'll see today, it depends on where you are on the Earth. The further you are from the Earth's surface, the less gravity there is. Again, that was from the video from yesterday. So, to think about this, these are posted up online. So if you missed something, you can go back and do that later. We can think about a campfire. So have any of you sat around a fire before? I'm assuming the majority of you have been around a fire. So we can consider a heat field. So there isn't really a heat field, but we can consider something about the heat field. So if we wanted to experience a larger amount of heat, what would you do? You get closer, right? So the closer you move to the fire, the more hot it is. If I'm standing at a set distance, and say the fire's over there by the cabinet, what would I need to do in order to experience a greater heat but not actually move? Make the fire bigger, right? If I put more logs on the fire, make it into a huge bonfire instead of just a little campfire, you'll experience greater heat. So that's essentially what I said here. I'm going to give you a sec to write it down. So you say, the closer we got to the fire, the field gets stronger. You experience more heat when you move closer. Similarly, the larger the fire, meaning the greater the flames, the bigger this is, then it says the further away we notice it, but essentially you'd feel a stronger field of fire if the campfire is bigger. Any questions with this? What does this have to do with gravity? Well, that's a good question. What do you think? How does this, thinking about a heat field, how would that help us in thinking about a gravitational field? The closer you go to an object, the bigger the gravity. What else? So the bigger the object or the more massive, the greater the gravity. Exactly. So a field of influence is affected by these two things: distance, size. So that's what we're getting at when we talk about gravity. Bigger the mass, bigger the gravity.
That's why the sun is very strong.
That's why we still orbit around the sun and we are not orbiting around the moon. Even though the moon is way closer, the sun has a much bigger mass. So it has a bigger force of gravity. Yeah?
But the mass of it, like the sun, right? The mass of it doesn't affect, or like the mass of the Earth compared to the moon, it doesn't affect the rate of the orbiting, or does it?
No, not really. I mean, there's a slight variation in the Earth's position due to the moon spinning around it, but it's not as much as the sun pulls it around. So this is the equation for a gravitational field. So G is our gravitational field strength equals force of gravity, you could just put Fg if you want, divided by m. I know it's weird with the underline. It's Fg divided by m.
Is this in the formula sheet?
Well, you already know this equation. Rearrange it and solve for Fg. Algebra, yeah. Given what we know about Fg from yesterday, we can get this equation. So this comes from the fact that yesterday we learned Fg equals capital G, capital M, lowercase m over r squared. So if I take this, divided by the small m, I get this. So this is our generic equation for the gravitational field strength. Mohammed, you with me? Okay, then you shouldn't be staring at your phone. Put your phone away, please. Thank you. So this is our gravitational field strength. Do you remember the other name for G? There's two definitions, two terms to talk about G. It's the gravitational field strength and something that you're familiar with. No. It's not gravity. No, it's not a force. So G is known as our gravitational field strength. It is also known as what? There's another term. If I told you on Earth, it's 9.8. No. No. G is also called your acceleration due to gravity. Exact same thing. Whether I call this gravitational field strength or acceleration due to gravity, same thing. Yeah, but you didn't know that. So I could tell you in a question, I could either ask for the gravitational field strength or I could ask for the acceleration due to gravity. You need to know what they both are. So I will use these interchangeably. You need to understand the difference between those. Actually, there is no difference. You just need to know that those two are the same thing. So notice with this, there's two units for lowercase g. Either it's newtons per kilogram, newtons divided by kilogram, or meters per second squared. You can use either of them. So you'll always need to include units on a test. If you're stuck with the units, look at your equations. G is force over mass, so it must be a newton over a kilogram. Or you can solve it using kinematics and get m divided by s squared. Yep, both are fine. Both of these units are fine. So let's try one of these. So as I said before, the Earth is not actually a perfect sphere. So if you spin a basketball, essentially the middle starts to bulge out as you spin it faster. That's what's happening with the Earth. So we want to calculate what is the acceleration due to gravity or gravitational field strength at these two positions. So on average, the radius of the Earth is given as 6.38, but it varies depending on where you are on the Earth. So these are just two variables for that. It's not a perfect sphere. It changes. Think about if you're on a merry-go-round. Thank you. If you're on a merry-go-round, what happens? You know the merry-go-rounds? Yeah. So what happens when you're on a merry-go-round? If it spins faster and faster and faster? It doesn't get wider. What happens to you? Yeah, but you tend to get pulled outwards, right? So as it spins, you get pulled outwards. So if you're talking about the Earth, think about the water that's on the Earth. If I spin the Earth, the water wants to stay in the same motion, it's going to expand outwards.
I have to understand. Why isn't the radius like less than half?
Yeah, but the radius is only the same everywhere if it's a perfect sphere. The Earth is not. Because if I'm spinning it this way, things don't get pulled up and down, they get pulled side to side.
So why don't I just calculate radius on the same spot every time?
Because it's different at different points. So if my Earth looks like this, okay, that's an over-exaggeration, but if it looks like this, my radius, distance from the center, here is going to be larger than the distance to the center here. So let's try calculating this. So at the North Pole, so if we're going to calculate for G, G equals capital G times M over R squared. Notice when I'm calculating this, I don't care about what is the mass that is at the North Pole. What mass am I using in this case?
What's the mass?
Yeah, I have a mass in this equation. What mass am I going to use?
The mass of the Earth.
Why? Because you're on Earth.
9.2.
And Earth is what's pulling the object down. So when I ask for what is the acceleration due to gravity, I'm looking for what is it of the Earth pulling on the object. So I'd like to give you a trick question where I give you the mass of something on the Earth. You need to know which mass to use.
So where do you get the 6.8?
I measured it. I measured it. I went from the North Pole to the center of the Earth and I figured out the distance.
So why did you
Why didn't you?
why did you divide it by 9.8 gravitation?
Because this is the distance between the surface at the North Pole to the center of the Earth. So it's not from the equation yet. This is just a value. Yeah. So I've got the numbers for this. G, capital G is just a number. It's on your formula sheet. This will always be the same. That's the one. So I'm not going to write this down in the equation because it's a waste of writing space. The mass of the Earth is, I think, 5.98 times 10 to the 24.
Mister, what's the value of the capital G?
6.67 times 10 to the negative 11. Again, it's on the formula sheet. Was I right? 5.98? Perfect. Every test. This one that you got on the last test is the formula sheet for the entire year. I will give you a brand new one that's not written on. So you have one to keep. I will give you a new one that has nothing on it. So you can write anything on your formula sheet.
So I mean, like the one you gave us before that stuff, you can use it on each test.
Yes. So you will want to practice typing this in your calculator because you will need to know how to get this and how to make sure you get the right number. So this is something that you absolutely need to practice. Yeah. But again, I don't know. Depends on how smart your calculator is. Some can do it, some cannot. All right, so this is what your acceleration due to gravity is at the North Pole. Yeah. So if I now wanted to do it at the equator, so now if I want to do it the other place, what changes? Yeah, so just, it's not the radius, you got to be careful. What does R stand for in this equation? It's not the radius. Yeah. R is the distance between the centers. In this case, it's equal to the radius, but R is not all the time going to be the radius. No, not in this case. No, it's not always the radius, because if I'm talking about two objects that are close to each other but still have like a rather large, so like for instance if I'm dealing with two masses like this, R is this. So it's not just what's the radius in here or the radius in here or the distance between those, it's center to center. So because we need to deal with objects that are really big, we are needing to use the distance between the centers. So let's finish this off and then I'll get to questions. So plugging in now the distance to the center here. So getting this, and then if you plug this one into your calculator and figure this out, so 6.386. Here we get 9.78. So what do you notice? What do you notice about these two numbers? They're close but not the same. What else? Yeah? Yeah, they have two decimal places, but that one's irrelevant. What? Both are 9s, yeah. What number are they both really close to? 9.8. Why is that important? So these are really close to the acceleration due to gravity. You've got an average of this that's 9.8. So that's where they get the number 9.8 from. Is they just take an average of the whole thing. So at the equator, this is going to be the lowest amount of gravity, or acceleration due to gravity. At your North Pole, it's going to be the highest. So in general, there's space in between those. So we just assume the Earth is a perfect sphere, and we say it's 9.8. So when we did that in kinematics, it technically wasn't fully correct. We made an assumption. So this is just something that you need to be aware of with your acceleration due to gravity. Yeah? You got what, sorry? This one? Yeah? Okay. What'd you put for capital G? What's that? G is 6.67 times 10 to the negative 11. It's on the formula sheet. It's on the back. So there's actually a number for G. You don't just put nothing in there. It'll be a very small change. I don't know. Depends on how much your mass is. It makes a difference. But yeah, if you were to measure your weight at these two places, your G is different. So your force of gravity would look different. So that's why it changes depending on where you are on the Earth. But very small difference, not a big difference.
So the radius and the distance in the formula are squared. That's radius squared, or
So R is the distance between center of mass to center of mass.
okay, and the R written in the column is the same thing.
So this is the radius of the Earth. But in our case, we're looking at, here's the Earth. What is our person, what is his weight at the equator? And what is his weight up here at the North Pole? So in this case, the center of mass is from here to here, and it's from here to here. So technically, I should have done the radius of the Earth plus the distance to the person's center of mass, but that's going to be maybe 1 meter compared to 637,000 meters. So if you add 1 to that, it's not going to make a big difference. So I just assumed it's basically this.
You got the question again, like at the root of the equation, do you have to do all this again, or can you just do like 9.8?
So in general, for forces, you'll always need to use this equation to solve it.
You have to do the equation?
Yeah. Yeah. Because often I'm not going to use Earth, because Earth is boring. You live here, it's 9.8. That's easy.
You have to do the equation?
Yeah. Any other questions on this? Yeah.
I thought the 6.67 11.
Okay. I can help you later with this one. It should work. One. Okay, this is the last example. And then I'm done. Yeah.
When the astronauts go into space,
Yeah.
the spaceship, there's no gravity. They can turn on the gravity.
So you're asking, is there gravity when you're out in space? Essentially, there is gravity. However, it's not as strong as because you're further away from the Earth. So the further away from Earth, you experience less gravity because you individually have a very small mass. And the force of gravity depends on both masses. So if we do the force of gravity is gmm, mass of the Earth is big, your mass is small. As opposed to mass of the Earth times the mass of the moon, much bigger pull between the two of them. So when you're in space, you will eventually fall to the Earth. Like the satellites are essentially falling, but because they keep going around, they orbit. It's a constant falling towards the Earth. So you still experience the force of gravity, it's just you're moving as you do it, so you don't experience it. If you take, say, the space station, if it's not in orbit, it's just sitting there, it'll fall to the Earth. Because it's still pulled. It's a smaller pull, but it's still being pulled. So it's based on the fact that they're orbiting, they're moving.
Is there a force
Yep. Yeah. If you're closer to the moon than the Earth, yes.
like this is the distance. It should be like the Earth without
Yeah. Yep, that's right. Yeah. So there's going to be a point in the middle of the moon and the Earth where you're in between and the gravity is the same. So you're neither getting pushed or pulled towards either one. Well, I mean, essentially what would happen is because things are orbiting and moving, like the moon orbits around the Earth and the Earth is moving, you wouldn't stay in that equilibrium position for long. You would eventually fall out of it and go towards one or the other. Sorry, just hang on a sec. Hey, fellas, I can't hear because you guys are constantly talking while people are asking questions. It's already hard enough to hear with masks on. Yes. Yep. Yeah. And if you look at the equation from the last page here, it makes sense, right? Because as r gets bigger, a bigger number squared becomes in the denominator becomes a smaller number. So yeah, the further away you get from something, the less gravity you feel. So let's give this one a try. We've got the moon is this far away from the Earth's surface. We want to know what's the Earth's gravitational field strength at that distance. So notice here I'm asking for gravitational field strength instead of acceleration due to gravity. But it's the same thing. The exact same thing. So don't get thrown off by gravitational field strength because I know out of all of here, maybe like 4 or 5 you will, statistically. So drill this into your head. Gravitational field strength, same as acceleration due to gravity. So no matter which one you are dealing with, it's the exact same thing. So we've got this. We've got a few tricks with this question. First, what is going to be capital G? Good. So you've got that, 6.67 times 10 to the negative 11. What is my mass?
9.61.
Mass. I'm looking for mass. I did G. Well, think about this. I've got the Earth and I've got the moon. Am I using the Earth's mass or the moon's mass? There you go. So, Kareem? So you are often going to be given a question like this. You're told 2 objects. You need to know which mass to use. So in this case, it's asking for the Earth's gravitational field. So your mass should be of the Earth. So this is on your formula sheet. You don't need to memorize this. I mean, you can if you want. You don't have to.
What did you do with the moon?
We don't care about the moon, actually.
What's the information?
We need to use the moon's as a reference point for a distance.
There's an asteroid that's shut
So yeah, so here's the thing. Whether I'm dealing with the moon at this distance, an astronaut at this distance, a pebble at this distance, your shoe at this distance, it doesn't matter what's at this distance, G is going to be the same. What matters is the distance and what's causing the pull. If I'm talking about force, yes. If I'm talking about the field strength, no. Because same thing with compared to the fire, right? So if the fire is burning at some distance at a set amount of heat that it's generating, doesn't matter if I'm standing here or your pet dog is standing here or your little sibling is standing here, will it change the amount of heat that's generated at this point? Right? Because no matter what's standing here, they feel the same amount of heat from that fire. So it doesn't depend on what's here to generate a certain amount of heat. How about the R value? What is my R value in this case? No. It is not this. I need center of moon to center of the Earth. So here's the moon, here's the Earth. Bigger one's the Earth, smaller one's the moon. No, this is from surface to surface. That's from here to here. Is that from center to center? No. So this distance is 3.85 times 10 to the 1, 2, 3, 4, 5. But it's in kilometers, so times it by 1,000, 5, so it's 8. Again, kilometers. I just did. Kilometers to meters. Times it by 1,000. You should know your unit conversions. This is pretty easy. So this, what else do I need to include in this? So here, this is the radius of the Earth. 6.38 times 10 to the 6. Just use what's on the formula sheet. Those of you who have your formula sheet, look at the back. Earth, mean radius just means its average radius. 3.38 times 10 to the 6. Yeah. 6.38. What did I say? 6.38. It's what's on here. So if I add these two together, is that my R value? I still need the radius of the moon. How much do you want to bet?
There's some Mars, Venus,
Yeah? And what does it say right underneath that box?
7.3 times 10 to the power 22.
That's the mass.
1.78 times 10 to the power.
There you go. Ten to the what? 6.
Mister, I didn't stop chemistry to come and find the significant figures.
I'm not doing sig figs.
That's a quick.
No, this is scientific notation.
Same thing.
The scientific notation and sig figs are two very different things. You think just because there's a times 10 to the power of something, you think it's sig figs?
Yes.
Okay.
We did too much chemistry.
All right. So if I want to figure out what the R value is, I need all of these combined.
So do we have everything?
So what's probably going to help is instead of putting this plus this all under here, it's easier just to add them all first. That's probably just going to make your life a lot easier. So all of this is the R value. All of it combined together.
If I add all the exponents and then add all the numbers, will it give
Nope. You need to add them all as they're added. You can't just add the, because it's multiplied. So if I did 3.85 plus 6.38 plus this, plus 10 to the 6 plus that, it will work. No.
Add the whole thing?
Add all of those together.
Would it make a difference if I put 385 instead of 3.8?
Yes, it'll make a big difference. You need to convert this into meters. You always need them in meters.
Oh, no, I mean like right now.
Do you need what, sorry? Okay.
We don't have to do anything by writing the moon and Earth because it's already in meters.
But once I just divided by no, that's what
We only have to take the 1.73 and 1.3 because
So this is going to be what the overall radius is. Good. Yes, it's not you this time, Mohammed. So now that we've got the total distance between the centers, now you can go about calculating this. So again, it's easier if you did that separately as opposed to doing it all together. And now you just plug it in your calculator.
What is the earliest?
I don't want just to visit
All right, so this is your final answer. You can pick either one of those to do if you want. So one of them is not in scientific notation, one of them is. I don't know why a bunch of you are trying to take pictures of this. This is going to be posted up online, and the completed notes are already up online.
Is it going to be posted up online with the Shahwata?
I don't think so. I forget if I put just the PowerPoint or if I put the completed notes. I don't remember which one I did. I don't remember. But you can find this online. Yeah, you're more than welcome to. This time it won't have the buzz like last one. Yes. I'm sorry for those who watched it and there's a buzzing in the background. Anytime I have my computer plugged in, it buzzes. I don't know why. It's the same thing when I was on Zoom with you guys, and if my computer was plugged in and I had my headphones in, it buzzed. So, I don't know why that is. Okay, so I'm going to at least stop the recording so I stop torturing everyone.